Today we'd like you to come away with, for those of you who aren't familiar with graphs, how they came to be, and a little bit about graph databases. We'd also like you to come away with some of the really unique characteristics of graph data that lead to the kinds of architecture patterns you see showing up in graph databases, like Neo4j. And leading to that, software runs on hardware, and one of the things that excites us about our relationship with IBM and with Power Systems is the convergence in terms of where that hardware platform has come and where it's going, and how Neo4j has come into being, and it's a very suitable and effective combination. So we'll talk about the way we've structured the time is I'll spend roughly 20-25 minutes talking through some background on graphs. For those of you who already know graphs, I hope to offer maybe a slightly different perspective and take on what you're familiar with. And for those who aren't familiar, I hope to talk a little bit about the portfolio view inside the organization and what they're good for. And then I'll hand off to Keshav, who will take you through, those of you who are not familiar with IBM Power 8, through the range of options from large servers to small servers and specialized I/O subsystems and so on. And then we'll talk about the combination of the two. So let's jump in. From at the super broadest level, what excites us is the fact that this combination of technologies allows you to solve massive scale problems that were previously unsolvable. This is about offering solutions to the business at an extremely large scale. And to put that into context, I want to take you back in time a bit. And if we go back to the era where relational databases really came into the fore, and you look at data management back in 1990, which is when I started doing work with data and databases, the big business problem at the time was you had still all these paper forms, all these manual processes, and you needed to get them digitized in some way into a computer system. The kinds of technology you were dealing with was very, very small and sparse amounts of RAM, which is also very expensive, as well as spinning disk, which is very low capacity compared to today, also very low in throughput compared to today, and also optimized for sequential I/O, meaning picking up bits on, the head picking up bits as they're spinning underneath the disk. And so the kinds of technology that emerged as a result of these requirements and constraints, it's no surprise it looked like this. The prototypical, database 101 example that you learn is taking an order form and applying a set of rules, normalization, breaking it up into several parts, and then the database engine is great about reassembling the things that you broke apart back into the thing you started with, storing that efficiently and providing query functionality. Probably all very familiar with that. And now let's look at where we are in 2016. We're in a very different place. First of all, the kinds of problems that the business is interested in solving look very different. All the interesting paper form, problems, that's no longer differentiating. That's bread and butter, and it's pretty much already there. What you have is these real-world systems that are rapidly changing, and the problem the business is faced with is trying to make not only make sense of all of that, but to be able to act in this dynamic context across all of the different touch points and channels. The memory situation has really changed. Now you can get machines with huge amounts of RAM, even hundreds of gigabytes, terabytes of RAM, even tens of terabytes of RAM at the ultra high end, and for thousands of times cheaper than it was back in the day. And from an I/O perspective, we've come a long, long way from spinning disk. And some of the key differences are not only is it faster and larger, but it's also much, much better optimized for random I/O, which is which opens up a lot of new and different possibilities from a database perspective. If I'm going to design a database that is optimized for randomly hopping all over the place, then all of a sudden I can solve different kinds of problems than designing a database that's designed to say, aggregate a number of like things, which is also useful, but this opens up a new kind of possibility. So if I were to design a database today and sit down with the tools I have, the hardware and software tools, to apply a solution to these real-world dynamic systems, the kind of model I would end up with looks a lot like this, where you have individual items with relationships, and this is how the brain is structured, and this is how the brain processes data. You have neurons connected by synapses, and small electric currents run through everything, and these gradients represent processing. And this is actually exactly how Neo4j works. And this is, of course, the most sophisticated computing and data engine that we know of, is the human brain. So if we can model a system after the human brain, you end up with something that's new, that's a graph database. And to put it into perspective, if you look at the database landscape, there's a great site called DB Engines, db-engines.com, that ranks popularity of different databases according to kind of the measures you would expect: Google Trends and LinkedIn skills and Stack Overflow comments and a variety of other things. If you look at relational databases, which, by the way, that flat line doesn't mean that it's not very much the largest the largest and most widely deployed and adopted technology. It's been around for 30 or so years, but the change in popularity has been relatively small over the last few years. And then you've got all these new exciting data technologies that a lot of you are probably using and or exploring, ranging from wide column stores to time series databases to search engines, etc. And one kind of database stands out among all of these. It's the graph database, for some of the reasons that I'm going to talk about. And in fact, if you go and look at what the analysts are saying, Gartner has this amazing statement saying that essentially the single most effective competitive differentiator, aside from getting data loaded into a database in the first place, is graph analysis. And graph analysis is a term they use to describe a variety of kinds of insight and activity involving the kinds of computing patterns that I mentioned earlier, very much like the human brain, sort of spidering through this network of connected things. Gartner also predicts by the end of 2018, roughly 2 years from now, 70% of leading organizations will have one or more pilot or POC efforts underway with a graph database. We of course, in Neo Technology, have quite a number of customers in production doing really amazing and meaningful things. And if you spend a bit of time on our website, or actually at graphconnect.com, where we just 2 weeks ago wrapped up an amazing conference that IBM also attended and sponsored, you'll see some great talks from some of those customers. And then Forrester estimates that actually by the end of next year, over 25% of enterprises will not just be doing pilots or POCs, but actually using graph databases. And if you go back to this DB Engine site and you drill down into graph databases, something we're very proud of is our role very early on in helping to develop and educate in this space. We're very proud of our role, not just as a software provider, but as a part of a broader community that we invest in helping to assist and curate and educate. And there are a lot of great things happening in the community on any given day. If you just look for Neo4j on Twitter or go to our events page, usually on any given day there are at least 2 or 3 events happening per day somewhere in the world around Neo4j. And if you actually look at Neo4j and the number of developers we have, the sort of amount of focus, it's equal to or greater than everything else that you see here combined. So we invest very heavily. We welcome and we feel it's great that to have other players in the space. That's an important part of the ecosystem too. But we're also very very, very proud of being able to help play a role in moving the space forward. I won't bore you with too much with the right side, but suffice to say that Neo4j has received a good amount of recognition from various quarters, both press and analysts. Gartner recently published their operational DBMS Magic Quadrant, and this is Neo's third year on the Magic Quadrant, and the year before that, Gartner named us a cool vendor. Let's take a step back and look at the portfolio view. So by this time, you might be saying, well, geez, there are so many different kinds of database technologies. How do I choose? And I think there's a simple way to look at these. It's how connected is your data? And if you start in the middle, where you probably are today, relational databases, as I mentioned, are great at pulling data back together that the model forced you to split apart through this normalization process. So they're kind of okay at joining data. You have joins, you have foreign keys, etc. But there are also, when you get to doing too many joins or too much recursion, relational databases tend, A, not to perform all that well, and then B, you can really get tangled up in trying to use the SQL language to express very complex relationship type queries. But if you go back to about 10 years to when NoSQL, or less than 10 years, when NoSQL was starting to come onto the scene, what caught people's attention wasn't so much the connected data that hadn't yet quite, that wasn't yet as mature. It was the fact that you had these ultra large problems that involved simple lookups, and where scale was the problem. Amazon published a paper on DynamoDB. Google published a paper on their big table technology, and these both involved cases where you had these massive scaling requirements, not just in terms of size, but in terms of number of queries. And those problems involved key value lookups, or a lookup into kind of a pre-computed canned query, which you would materialize in the form of kind of a denormalized column family with some schema flexibility. So the three kinds of NoSQL you may be most familiar with, document, key value, and column family, all fit into the category on the left, where those technologies make fundamental trade-offs in order to be able to solve the kind of problem I just described with discrete data, with data that's not connected. One of the trade-offs is ACID, so being a little bit looser with one's notion that data has committed. Another is the trade-off of relationships. I remember going to my first Cassandra meetup in 2012 as someone with lots of relational database experience, and coming away actually pretty amazed that someone could have built a database that doesn't have any architectural support for joins, and that had to be done in the application layer. On the right side, you have a completely different kind of requirement and a completely different kind of architecture that emerges to support it around connected data, where ACID is important, because if I update something and update a relationship, then I need to make sure the node at either end is either connected or not. If it's in limbo, then that can lead to really misleading results, and corruption can cascade in a pretty disastrous way across the graph. You also have lots of performance optimizations around being able to do this ultra fast in-memory pointer chasing to follow your relationships. And you also have a language designed to very easily formulate what in the relational database world would be very complex queries. And another portfolio perspective is you're probably used to hearing a lot about Hadoop and sort of big data in the context where data scientists and analysts are looking at data, doing reports, coming up with algorithms, doing back testing. And if you put all that kind of on the left side and say that's all insight, it's deriving insight from my data, then what's also really important is being able to put that insight into action. And the classic IT pattern for putting insight into action has been through batch, overnight kind of pre-computation. And the new world that we've now entered and what's possible today with Neo4j and for these ultra large problems with Neo4j on Power is being able to have your action take place and be calculated in real time across websites with tens of millions of active users at an ultra large scale. So if you think about this virtuous cycle between insight and action, one of the things this technology is capable of is closing the loop and making these complex computations in real time to get better recommendations, better fraud detections, better intrusion detection, better master data management of complex hierarchical data, and so on. I'd like to talk to you a bit about the technical requirements so that you can understand the architecture a little bit better, and why you need a different kind of database for these kinds of problems. If you look at relationship-based queries, what you find is single queries can touch a lot of data. If I want to do a friends of friends query, Kevin Bacon kind of thing, or which is useful like in an IoT kind of scenario, what's the shortest path between these two components? That can actually touch a huge amount of data, and that can bring a relational database down to its knees, let alone another NoSQL database that doesn't even have the rudimentary relationship constructs that a relational database has. The second is that queries can take non-sequential arbitrary paths through data. This is a fancy way of saying it can hop around all over the place and do lots of random I/O. So if I go back to that picture you saw on the bottom right, where today's I/O subsystem, like IBM CAPI Flash, for instance, is super well optimized for lots of random hops, you can start to see how these two things would go well hand in hand. Another one is that when you're running real-time queries, not only do you need your response times to be very fast, you need them to be very consistent. And then another is that queries need to run reliably with consistent results. Well, you might look at me and say, well, duh, it's a database. Your job is to be consistent and give me consistent results. However, remember, we're in a new era of databases where for the last 3 years, there's been a new database popping up maybe every week. And the general rule, Kurt Monash has a great rule of thumb that to the effect that it takes 5 to 7 years and tens of millions of dollars to build a reliable database that's actually usable in production for anything at all. And by the way, cardinal rule number 2 of database development is that there are no exceptions to that rule. So the fact that you have new databases coming into being that might have been written by just a handful of people, that's exciting, that's great, but there's a lot of maturation time that takes before you can get to the point that you can trust your data in a database. Not just that, but some of the architecture patterns that I talked about earlier make conscious trade-offs. Those conscious trade-offs may be appropriate for when you're dealing with individual data, but when you're connecting things, those trade-offs no longer work. Those trade-offs lead to data corruption. If I look at traditional architectures and how they measure up, and I guess the bottom right is more meant to reflect not the traditional stuff, but some of the newer things, you'll see the challenges. And so if I drill down into performance, you look at a typical query. If I'm going to program my NoSQL database to run, say a document database to run a data relationship query, you'll end up landing doing lots of hops over the network, not being able to pointer chase and do millions of hops per second per core like you can with Neo4j on Power, and so you end up with not being able to fulfill queries in real time. It's also a very inefficient use of hardware. You often need 10 times more hardware to not even be able to accomplish the requirement. Whereas if you look at what happens if I can take all that data in memory into an architecture that's optimized for this particular problem, then you end up with these super fast real-time queries. I'm going to take you through a few more things and then hand over to Keshav. I want to talk about a couple of tests done actually on very modest hardware, not your ultra large stuff, just to give you an idea of how powerful this is. And chances are, you can get literally these kinds of rates on laptop size hardware. Of course, it all depends on the size of the data set, and this is why having a range of options like you have with Power is we feel a good thing. So we got this realistic retail data set from Amazon with hundreds of thousands of products from a public data set, and ran a social recommendation, something like, and this is actually expressed in Neo4j's query cipher query language. You can see things or nodes enclosed in parentheses, and then relationships. So you bought something, and then someone else bought something, and that someone else bought other things, and those other things are what I want to recommend. So that's a significant, it's a simple multi-hop query. Expressing this in SQL is quite a bit more complex. Here I've expressed it pretty easily. But then if I run these across 1, 10, 20, 30 threads, and you'll remember this when you hear from Keshav how many threads you have per core and how many cores you have per server. This can be done on a single socket. You can end up with tens of millions of threads per second, tens of millions of hops per second, creating this combined capability of ultra fast, ultra efficient, ultra sophisticated recommendations. If you look at loading data, there's a high performance loader that can load millions of records per second. So 1.8 billion relationships took around 20 minutes with another public data set. And the good news as far as where all this is, where hardware is going, is there's a well-known Stanford professor, Yuri Leskovic, who this year gave a really interesting talk that I actually attended, where he looked at all the largest graph data sets out there and how large they were and how many would fit in RAM. And he came up with this saying for big RAM is eating big data when it comes to graphs, that the growth of memory has occurred at such a large rate that the majority of interesting enterprise data sets can fit into RAM on large machines. And then to the degree that you bring in more and more data from outside and it doesn't fit in RAM, then then you need a really fast I/O subsystem. And guess what? There's a solution to that. Running a little short on time. Use cases. There are a number of use cases that can be used inside the company, a number that can be used in your customer-facing applications. I'd encourage you to, if this is of interest to you, to explore Neo4j's website. There's a use case section. As I get into people, places, things for the most basic recommendation, to interests, to transactions, to activity, you end up scaling much, much, much larger. By the time I get to activity and clickstream and that sort of thing, there's so much data involved that you really need, there's a substantial need for tuning and scaling, and this is where the right hardware platform can play a role in the right architecture. Same with fraud. Very big problem for not just financial services companies, but every company. And a lot of the kinds of frauds that happen are not like this. This is simple fraud that every company is equipped or should be equipped to handle, looking at out-of-band activity. What's harder to tell is when you have sophisticated networks of fraudsters who collude and stay inside of the band. This is the kind of thing that can be used to help prevent fraud and detect fraud. There's a well understood spectrum of fraud analysis that can occur. Entity linking is the one I'm talking about at the far right. So that said, now hopefully that gives you a good overview of Neo4j and graphs in a nutshell, and sets up some context for the architecture that Keshav is going to introduce us to now.
Thanks, Philip. Hopefully, everyone can see my my screen now. All right, so let me get going. Again, thanks, Philip, for the wonderful introduction there on Graph and Neo4j. Just a quick intro. I'm Keshav Ranganathan, and I'm the offering manager for Power Systems Data and Analytics Solutions at IBM. Really excited to be part of this joint webinar with Neo4j to highlight the value delivered by Power Systems for building a high-performance, scalable deployment platform for Neo4j. So over the next 15 to 20 minutes, I'll first get into a very high-level overview of Power Systems portfolio, especially for those that are that have not been introduced to this platform. And then we will highlight a very unique price performance optimized deployment platform for Neo4j. And we have some interesting performance numbers that we will share in this call, as well as some price performance data. And we truly feel like this platform changes the paradigm around how you process very large graphs that do not fit in memory, especially from a price performance optimized fashion. So with that, let's go to the next slide. So here, this is a very quick introduction to core capabilities of Power Systems and the broader ecosystem that enables really breakthrough performance, not just for graph databases, for a number of different big data and analytics workloads. So when we introduced Power 8, which is our microprocessor that is part of the IBM Power Systems portfolio, it was truly designed for big data and analytics workloads. So when we talk about that, what do we mean by that? We are looking at what would be a balanced system design for a variety of different big data and analytics workloads, and that includes having sufficient processing and compute capability, having sufficient memory capacity and bandwidth. The third piece would be around processor cache and latency, and finally I/O bandwidth. Basically the ability to move data in and out of the system at rapid speeds. And again, when we talk about big data and analytics, it becomes really crucial. So if you look at the differentiation, we have almost 4 times the number of threads per core as commodity infrastructure. Basically, what does this mean? If you go back to what Philippe mentioned, as you scale the number of threads, you can drive more database operations, and when you are operating under stringent time constraints, having this ability to run concurrently across multiple threads results in delivering the insights that you need very quickly. The second piece is around memory bandwidth. Again, goes back to the core systems requirements for a balanced system for big data and analytics. we have almost 4 times more memory bandwidth than x86. We also support more or higher memory capacity on our servers. So, for example, I'll get into this a little bit later in this presentation. For our scale-out systems, we can go all the way up to 2 terabytes, and then for our enterprise systems, we can go all the way up to 32 terabytes of memory. So, pretty large or capacity. The third piece, this is really crucial, right? I mean, we have almost 4x more cache per processor and at a lower latency than other competitive platforms. Basically, this allows us to handle larger chunks of data at much higher speeds. Frankly, a very robust cache design is an important factor that impacts transaction latency. So, for example, if we are running all the instructions and data from memory versus what you would gain by having that in level 1 cache, we are talking about almost 800 times slower. So even having all the data in memory, moving it into the processor and then processing it is especially into level 1 cache, you're going to have 800 times slower results, right? When you look at Power 8 design, there has been significant focus on this cache design. We have 3 levels of on-chip cache, as well as a 4th off-chip cache that is on the memory cards, and basically this drives significant advantage in terms of performance for a variety of big data applications on power systems. So in addition, we obviously have a pretty good I/O ingest rate, in terms of moving a large amount of data in and out of the systems. So that talks to the technical capability, right? I mean, the technology that we are delivering. The other key innovation is around what we call as open innovation or collaborative innovation. So we understand that we need to leverage the whole stack in terms of delivering value to our, at the application level to our clients. And it's not just the processor that can do this. And we need to drive innovative solutions across the stack, and we do this in partnership with our industry partners. So Open Power Foundation was established in 2013. This was an open technical membership organization, and the idea was to create an ecosystem that will accelerate innovation on this platform. So whether you're talking about pure innovation or acceleration through GPUs, FPGAs, advanced I/O, platform optimization for software, advanced hardware technology, a number of different work streams are part of this Open Power Foundation. In fact, we started this with 5 members, IBM, Google, Mellanox, NVIDIA, and Tyan, and now we have grown to almost 250 plus members. So in addition to the core technology that we bring to market, we have a robust collaboration with a number of partners to further enhance this platform, and we'll talk about that a little bit more here. So if you look at, I mentioned the 5-member organization, it has grown to almost 250 members, and again, in terms of Neo4j and in terms of looking at open source databases and other applications, we now have almost 2,500 plus Linux ISVs developing applications on Power, and more than 100,000 plus open source packages. So this is a really vibrant collaborative platform, and you're going to see even more innovation being delivered by IBM and by our partners in the space. And just to emphasize the set of partners and the various elements of the system stack, it's not just at the chip level, but it goes all the way from the chip level to software, system integration, and into research. So a pretty robust set of capabilities being delivered and being developed on this Power platform by both IBM and our partners. Let me jump to a view of our portfolio, right? So we offer a pretty broad set of servers. Many of you probably know Power Systems is offering, high-end, large S&P servers. We have a huge breadth in terms of not just those enterprise type of servers, but all the way into what we call as the scale-out servers. So if we start at the top with our enterprise server offerings, these models are really designed for enterprise computing. Some of the most complex mission-critical priorities that businesses have, these are systems that are supporting those priorities. Very innovative in terms of reliability, availability, serviceability features, so that eliminates unplanned downtime. I mean, these are systems that need to be running 24/7, 365 days a year, right? And on top of that, there are a number of features around capacity on demand, enterprise pools and such that allows workload consolidation, and more importantly, keep applications running even as the need for capacity grows. So focused on enterprise computing, right? I mean, these servers, right? I mean, these E880s to the E850s can go all the way up to 192 cores, and up to, like, say, 32 terabytes of memory. Now, more interestingly, in the recent past, is our portfolio around what we call as the scale-out family, right? I mean, these are 1U, 2U, or 4U form factors, and we offer, either a single socket or 2-socket servers. This includes, again, there are a set of servers that supports all the operating systems that we have, AIX, I, and Linux, but we have a very unique set of servers that are fine-tuned for Linux. These are, these make an ideal foundation for a number of scale-out and cloud environments. Now that's part of the scale-out portfolio. Again, designed for big data, very scalable, very economical in terms of handling the big data and analytics workloads. Especially there is a new line of servers that we introduced earlier this year and refreshed it just this quarter, called the LC line of servers. And again, these servers are built on top of some of our collaborative work as part of the Open Power Foundation that I mentioned earlier. And again, critically important, these servers now has changed the game in terms of even price point at which you can acquire power systems. These are very competitive, both in terms of performance, but they're also very price competitive. And again, depending on the configuration, in many cases these are equal to or lower than equivalent x86 configurations. From a Neo4j perspective, again, between the scale-out servers and enterprise family, depending on what you're trying to achieve, what type of systems you have, we could look at both as viable deployment platforms. But with the next few slides, I'll be talking about a very unique option built off the scale-out portfolio that offers a price performance optimized platform for Neo4j. So we'll get to that shortly. So let's get to, again, this slide talks to our commitment to Linux. Every one of our servers in the portfolio supports Linux, starting from infrastructure as a service platform all the way to our scale-up portfolio. We support Linux, and again, this goes into the platform that we can use to deploy Neo4j. One of the key capabilities that we have in support of this platform for Neo4j is called CAPI, and I'll briefly talk about CAPI, which is a very key innovation, very unique to Power 8 architecture. So what does CAPI do? It basically provides very high bandwidth, low latency path between external devices, whether these are accelerators or storage and networking devices, to the power core and the memory architecture. So CAPI removes the overhead and complexity of the I/O subsystem and allows any type of accelerator to operate as part of the application. So basically we have it makes it much more easier to add additional accelerators to system that operates as part of the Power 8 processor. So the way that we did this was using a dedicated part on the chip called the CAP, which is the coherent accelerator processor proxy, and then we also provide a power service layer which sits on the FPGA. Basically makes it much more simpler to develop accelerators and to attach accelerators to power systems. And in fact, just earlier this month, we announced the next generation of CAPI called the OpenCAPI project. You can learn more about it in the opencapi.org website, where we are partnering with a number of players to drive CAPI much more broader than just IBM. Again, in the spirit of partnering with the industry players to drive innovation. So what does this mean, right? I mean, why do we need CAPI and what does it do, right? I mean, so here is a very simple view. Like I mentioned before, this allows an external accelerator to act very closely with the power processor core, and we basically eliminate a number of device driver overhead for attaching an external accelerator. So typically, if you have an accelerator without CAPI, there is a lot of setup that is needed for moving the data from the processor to the to the accelerator engine. Basically, CAPI removes these overhead. So accelerators basically participates in terms of handling locks or in terms of accessing the memory as a normal processor thread. So significant advantage in terms of attaching an external device or an accelerator via CAPI versus just a simple PCIe connection. What did we do with this, right? I mean, so what we did was we used this CAPI capability to develop this unique platform called the IBM Data Engine for NoSQL. This is an integrated platform for large and fast-growing NoSQL data stores in general and Neo4j in particular, right? So we basically leverage the CAPI capability to provide a high-throughput, low-latency connection to flash storage, right? And this creates a unique new storage tier that helps address some of the scaling and performance challenges with databases that needs to keep large amounts of data in memory, or that benefit from having large amounts of data in memory, and basically helps drive performance advantage. So if you look at the platform, we have two different options. One is called the external configuration. In this case, we allow we basically allow an external IBM Flash System 900, which has a capacity of up to 57 terabytes, to be attached via CAPI to provide this super fast, low latency storage option. And we recently introduced what is known as the integrated CAPI Flash configuration. And in this case, you don't need any external storage. We basically have a couple of flash sticks up to 2 terabytes in capacity right on the card. So, and depending on the server option that we choose, you can either get anywhere from 2 terabytes all the way up to 8 terabytes by adding up to 4 cards on the server. So you can either have a CAPI-attached external flash configuration that can scale up to 57 terabytes, or you can use the integrated CAPI Flash that provides on a single card up to 2 terabytes, and with multiple cards that can be added on these servers all the way up to 8 terabytes. So this is we view as a pretty big game changer for deploying a number of NoSQL databases, but Neo4j is a great option on this platform. What does it mean, right? I mean, why do we do this? There are a couple of key reasons. Number one, we have almost 3x better IOPS per hardware thread with this option. So attaching Flash via conventional I/O versus attaching it with either the integrated CAPI Flash or with an external CAPI Flash configuration, we can drive almost greater than 3x better IOPS per hardware thread. And the second piece is we remove some of the processor overhead in terms of managing the I/O, and that really helps allocate the processor for handling other application requests. And the second piece is it's a much more lower latency in terms of how quickly you can access the data, and that again helps position it as a significantly better storage tier than a traditional PCIe attached flash. I want to briefly now jump onto a performance workload that we ran. This is pretty significant. So we worked with Neo4j on a very unique or I should say an internal workload that mimics a typical real-world graph transaction workload, and we used Power 8 with 20 cores, 128 gigabytes of memory, and we attached a single card with 2 terabytes of extended flash storage, super fast flash storage attached via CAPI, and we compared it to an Intel configuration with about 24 cores, same amount of memory, and with 2 terabytes or 1.6 terabytes of NVMe flash. And again, the way we tried to exercise this, the I/O, was to take a 200 gigabyte data size, right? So there is the data doesn't fit in memory, so there is data that is on the flash. And what we see is in terms of throughput, we have an 82% more throughput than x86. So significant performance advantage, and what we expect is, especially for even larger data sets, right? I mean, even larger data sizes, especially if you go to a terabyte or more, this platform will provide a significant performance and more importantly, price performance advantage for processing graphs. So if you look at the next slide, in addition to the performance advantage, for when we look at a price performance, when we take the Power 8 server capability plus the CAPI card that includes 2 terabytes of flash versus say a competitive x86 platform, we have a 1.61x price performance advantage. So this definitely provides a significant game changer in terms of deploying large graphs. From a price performance optimized platform perspective, we truly believe that this is a unique platform. You can start with maybe small amount of data. Maybe it even fits all in memory, but as your data size grows, by adding this single card, now you have significantly scaled up what the amount of data that can be handled by that single server. You no longer need to add more memory or look at a bigger box. We have sufficient processing capacity to handle even larger data sizes by just adding this card. So that's our key unique value prop. So again, going back to the original slide that Philippe put out, right? I mean, so if you look at what is the value prop, basically Neo4j on Power 8 offers unparalleled scale and performance, right? I mean, we are bringing together the strength and tooling of Neo4j for managing and extracting insights from data relationships via a very powerful graph database, and the performance and scalability of Power Systems with CAPI-attached Flash. So we are truly excited jointly in terms of what this brings to our clients. I mean, so the other part is, in addition to this performance, the TCA advantages and price performance advantage, we have an ongoing partnership with Neo4j where we are looking at what are the ways to further enhance performance, but further enhance how easily these solutions are consumed, looking at how we can deliver integrated solution that makes it much more simpler to acquire and deploy Neo4j on Power Systems. So we expect to have additional announcements around how we make it easier for our clients to acquire this technology, the Neo4j on Power technology. Just to wrap up, we have provided some additional links and contact information in terms of how you can get in touch with us. There's a lot of information that are available on both the Neo4j website, specifically around graphs, but also our IBM Power Systems website. We also have the data engine for NoSQL web page. There are solution briefs and additional details on the value delivered by this platform. We have provided a couple of key email IDs. If you have any questions or comments, if you want to reach out to us, feel free to email us.